Hello there, how are we doing? Hope all is well. Here we are with our 4A notes. So these are applications of exponential functions. So how are we going to use these exponential functions to model growth and decay? So just like you saw in last week, we have our exponential growth and decay models. Growth, remember, that's going to have a base that's bigger than 1, and then a decay is going to have a base that is between 0 and 1. So we had practiced rewriting those exponential functions in the form of y equals a times b to the x into these models right here. So if you're saying a 1 plus some number, that's going to be a growth because that's a number bigger than 1. And then if you see 1 minus some number, that rate, obviously that'll be a number less than 1 but bigger than 0, so that's going to show your decay. So nothing new here. So now we're going to be provided some word problems, and we're going to have to come up with that model and determine if it is growth or decay. So our first example says, the value of a car in thousands of dollars can be approximated by the model y equals 31 times 0.92 raised to the t power, where t is the number of years since the car was new. So the first thing we want to decide is this showing growth or decay? Well, my base is 0.92. That's a number that's less than 1 but bigger than 0, so this is showing decay. And what I could do right here is I could actually rewrite this so that it looks like 1 minus some number now that we know it's decay. So 1 minus what gives us 0.92? Well, that would be 31. That a value doesn't change. That's our initial amount, times 1 minus 0.08 raised to the t power. That's the same exact thing as 0.92, 1 minus 0.08. The reason we want to do this is because now we can clearly see what that rate is. Remember, the rate is always going to be written as a decimal. So it's the rate as a decimal. Okay, and then you knew that A, I'll just write it right here, was that initial amount. So in this particular problem, if A is our initial amount and it's 31, then that tells me that that is going to be the value of the car when it was brand new. And because it's in thousands of dollars, that means that this car brand new was worth $31,000. Okay, and it makes sense that this is going to be a decay model because once you buy a new car, then the value just depreciates over time, right? The value of it decreases, it decays. This is telling us that it decays at an 8% rate. 8% decrease. How do I know it's 8%? Because that R value is 0.08. Moving that decimal 2 places to the right gives me the percent, so 8% decrease. For the third part, it says estimate when the value of the car will be $96,000. Well, that would be our Y value. So essentially we're saying 9.6 equals the 31 times 1 minus 0.08 raised to the t power. Maybe you're thinking to yourself, why did you put 9.6? Well, remember, this is all in thousands of dollars. 31 is in thousands of dollars. So if it's 9,600, that would be 9.6. Okay, our goal here is to solve for t. That's the time, the number of years since the car was new, and that's what we want to find. Estimate the value of the car, estimate when the value of the car will be $9,600. Well, we don't have the skills to solve this algebraically yet. That's what we're going to get into next week and in week 5 and 6. That's going to be using something called logarithmic functions. But right now what we can do is we can solve this by graphing. Okay, so if you're using your Casio emulator, that's on that VM Horizon software that you can download on your iPad. I think there's a video posted on how to do that. Or if you're using Desmos, or if you have a TI calculator, whatever the case may be, you would want to graph this, okay? So what you'll do is you'll graph this in two different ways. On the TI, you can graph this as one of your equations being y equals 31 times 1 minus the 0.08 raised to the x power. And the other graph, or the other equation that you could put in, is just y equals 9.6. So on that TI, you'll see two graphs, one for the representing the $9,600, the other one representing the decay model for this vehicle. And what you'll want to do is you'll want to find where those two values intersect on your calculator. So you could go to calculate, intersect, and you can find them where those two lines intersect. And that is going to be approximately at 14 years. If you're using the Casio emulator, this is going to be one of those times where you want to G-solve and do either the XCal or the YCal. So you'll plug in your equation, y equals 31 times, you could put 1 minus 0.08, or you can just put 0.92, it doesn't matter, raised to the x power, and you'll graph it. Because you know the y value is going to be 9.6, that means you want to do an x calculation. You are trying to figure out the value of x when you know the value of y. So when you graph that formula, you'll go to G-solve, you'll arrow over to see more options, and you'll hit the XCal. When you hit XCal, it should ask you, what is your y value? For the y value, you'll put in 9.6, you'll hit enter, and then you'll see that the x value is going to be, or the x coordinate, I should say, is going to be like 14 point something, like it's like 14.02 or something like that. So we'll just say approximately at 14 years, that's when it's reaching a value of $9,600. In example 2, it says in 2000, the population of a city was about 1.04 million. During the next 14 years, the population increased by 2.05% each year. So obviously we know this is showing growth because the population is increasing each year. And so it says write the exponential growth model by giving the population y in millions t years after 2000. So what is our initial amount? What is the population of the city in the year 2000? Well, that's 1.04 million. So let me change colors. How would we write that? Well, y is going to give us our initial amount of 1.04 million times, we know that this is a growth model, so we're going to write it in the form of y plus some number raised to the t value. What is that number? How much is it growing each year? It's growing 2.05%. Well, how do we write that as a decimal? Because r always needs to be written in the form of a decimal. So if we have 2.05%, then that is the same thing as 0.0205. So that's what I'm going to write right here, 0.0205. So this is showing me my initial amount is 1.04 million. My rate that it's increasing or growing every year is at a 2.05% rate. And then T is representing the years after 2000. So in part B, it says estimate the city's population in 2008. Well, how many years after 2000 is that? That's 8. So our T value is going to be 8 here. So T is equal to 8. So now I can just plug in that value. Y equals 1.04 times 1 plus 0.0205 raised to the 8th power. I can plug that into my calculator as is. 1.04 times the 1 plus 0.0205 raised to the 8th power is going to give me approximately 1.22 million people. That's the population in 2008. So it's obviously grown. Started at 1.04 million, now we're at 1.22 million people. Part C, it says estimate the year the city's population was 1.3 million. Okay, so that's a little bit more than what we just got. So we know it's going to be after the year 2008, right? Because it needs to get higher. So that is our y value. 1.3 million is the y value that we're trying to achieve. Our initial value, the rate of growth. Now I want to know what t value is going to give me that population of 1.3 million. So this is the same thing we did in number 1, part C. So depending on what kind of calculator you're working with, if you're working on the TI, you'll enter in 2 graphs, One of them will be 1.3. That'll give you just a horizontal line. The other one will be put in as the 1.04 times the 1 plus the 0.0205 raised to the x power. You'll find the intersection where they cross, and you'll get your answer there. If you're using a Casio, you can just plug in the y equals 1.04 times 1.0205 raised to the x power, and then you'll do GSOL. Again, this will be an x calculation because you know your y value is going to be 1.3. You're trying to figure out what is the x value that is going to give me that y value. And so when you arrow over, you hit x calculation, you'll enter in the y value of 1.3, and then you should get a t value or an x value of approximately 11 years. Okay, which makes sense for this problem. Like I said, if we knew that in 2008 the population was 1.22, to get a population of 1.3 is going to have to be a number of years after 2008. So 11 makes sense. And then it says estimate, just, FYI, it says estimate the year the city's population was 1.3 million. So would your final answer be 11? No, your final answer would be in 2011. Example 3. The amount Y in grams of the radioactive isotope barium-140 remaining after T days is Y equals A times 0.5 raised to the T over 13th power, where A is the initial amount in grams. So what I'm going to do first, before I read part A and what it's asking for, is I just want to rewrite this equation, this function that they give us, so that it looks like one of those growth or decay models that we've been using so far. So what I can do is I can say, well, this is the same thing as Y equals A times 0.5 raised to the 1 over 13 power raised to the T. This is what we did last week, just rewriting. And so now in my calculator, I can actually evaluate what is 0.5 raised to the 1 over 13th power. Well, that gives me 0.948. So now that I'm looking at this, I can decide, is this a growth or decay model? It's decay. Why do I know it's decay? Because my base is a number less than 1 but bigger than 0. So now I can rewrite it so that I can easily identify the rate at which it's decaying, and that would be Y equals A times 1 minus 0.052 raised to the T value. 1 minus 0.052 is 0.948. Those are the same exact things, but now we can identify what they're asking in part A. What percent of barium-140 decays each day? 5.2% decay each day. I'm seeing that right here. That's my rate as a decimal. Move it 2 places to the right. I get a 5.2% decay. That should have been a problem that you probably could have done last week. Okay, so now we're going to talk about compound interest. If you looked at the enrichment folder for last week, there was a couple of videos on compound interest and what it looks like and how is it beneficial to you to know this information when you go to start opening savings accounts or checking accounts or whatever. If you come into a lot of money and want to invest it in some kind of way, it's important to know those interest rates and how it's compounded. Okay. So first, what I'll do is I'll do this how compounding interest works as an example, and then I'll talk about what's in the box. So let's say you have $100 with 10% interest. You'll be very, very lucky to see that. I don't think I've ever seen that in my adult life. Times are just not that good anymore. But just, it's easier numbers to work with to show you for the sake of the problem. So what is that going to look like if it's compounded yearly? Well, let's take it year by year. In year 1, we have our $100, right? And then 10% interest. Well, what's 10% of $100? That's $10. So we get our $100 plus our $10 of interest, giving us a total of $110 at the end of year one. So that $100 grew $10, and so we have $110 at the end of the year. So year two rolls around, and what are we starting with now? We're starting with that $110 plus the 10% on that $110. Well, 10% on 110 is now $11. So at the end of year two, we now have $121. So year three, what are we starting with? We're starting with our $121 plus what is 10% of that? That's $12.10, giving us a grand total of $133.10. That's how. That's what it would look like if you were compounding yearly. Okay. If we were compounding quarterly means 4 times a year. So every 3 months, it would be 4 times a year, right? So how does that work? Well, in quarter one, we have our $100 that we start with. The $10, that is at 10%, so 10% of 100 is $10, right? So the this is the percent, the rate. So 10% divided by 4. Why divided by 4? Because I'm only getting a fourth of it at every quarter. So what is that? That would give me $102.50. So now that's my new starting point for quarter two. $102.50 plus the 10% divided by 4, because I'm only getting another quarter of that. That's going to give me $105.06. So I take that initial amount now with quarter three, $105.06 plus another quarter of my interest is going to give me $107.69. Then I take that initial amount, $170.69, and I get my last quarter of that interest rate, and I get $110.38. This is all in 1 year. 4 quarters in that 1 year. So at the end of year one, compounding quarterly, we get $110.38. Whereas if we were just compounding yearly after year one, we only got $110. Now you may be thinking to yourself, well, 38 cents, that's not a huge difference, like whoop-de-doo, extra 38 cents. But imagine that you're not just investing $100, but maybe 1,000 or 10,000 or, 500,000 or whatever. Okay, that could make a big difference. And especially over time, if you're compounding it quarterly, not just for 1 year, but for 10 years. Okay, that's going to have a way bigger impact than compounding it yearly. Okay, so let's now look at the box that says compound interest. Just want to go through and talk about what each individual piece of that stands for. So if you notice, it looks very similar to the exponential growth and decay models that we used earlier. So A is going to be the final amount that you're getting after this compound has interest. So that's going to be whatever your principal is. That's your starting amount. For this particular problem, it was the $100. My principal amount is like the initial value, okay? It's going to be 1 plus R over N. R is your annual interest rate. So in this particular problem, it was 10%. N is the number of times you're compounding in the year. Well, if you're compounding yearly, that's just 1 time in that 1 year. So anything divided by 1 is just that rate. If you're compounding quarterly, then that's 4 times in a year. So that rate divided by 4. If you were compounding monthly, there's 12 months in a year. So that would be the R divided by 12. If you were compounding daily, there's 365 days in a year. So it'd be R divided by 365, etc., etc. Why is it 1 plus? Because all of these are going to be growth models. You're just gaining interest. You're never going to lose that interest, right? You might not gain a lot, but you're never going to lose anything. All of that is going to be raised to the n times t power. N is that same number of times that it's compounding in the year. So whatever you're dividing your rate by, you'll also be multiplying that to the number of years in that exponent, okay? So let's go ahead and try to put this together in a new problem. Example 4 says, you are deciding between two accounts to deposit $10,000. One pays 1.6% annual interest that is compounded daily. The other pays 1.68% annual interest that is compounded quarterly. Which account will yield more after 5 years? So I want to check out both of these options, right? So on the left-hand side, I'll do the compounded daily. So this will be my daily. And then on the right-hand side, I'll talk about the one that's quarterly. Okay. So first thing I will do is I want to write the function given this information. So account 1, that's compounded daily, it's only going to pay 1.65% annual interest rate. My principal amount, what am I depositing, is $10,000. So that means A, my final amount, is going to be my principal, $10,000, times 1 plus, what is my rate? What is my annual interest rate? That's 1.65%. How do I write that as a decimal? That would be 0.0165 over. How many times is it going to be compounded in that year? Well, if it's compounded daily, there's 365 days in the year. And so that'll be raised to the 365 times t. T is the number of years. Well, in this particular case, we're worried about how much money we're going to get after 5 years. So that'll be 365 times 5 because that's the value of my t. I can plug this straight into my calculator. Okay, be careful with your parentheses and how you're inputting this. But when you plug that into the calculator, your final amount that you get will be $10,859.97. So over those 5 years, you got an interest amount of that $859.97. So you made some money after those 5 years. Cool. Well, let's see if quarterly is going to be a better bang for our buck or if it's not going to give us as much as compounding daily. So over here, I'll do the same thing. We want to know our final amount after our principal amount, $10,000, is compounded. So 1 plus, what is our rate for the second account? It's a little bit higher. It's 1.68. So writing that as a decimal would be 0.0168 over how many times is it going to be compounded in the year? Well, if it's quarterly, that's 4 times a year. So divided by 4, raised to the 4 times 5. 5 is the number of years. Okay. So again, I can plug that straight into my calculator. And when I hit enter, I should be getting a final amount of $10,874.38. So which one is giving us more after the 5 years? The second account. A little bit of a higher interest rate, compounded less. So you would think that that 0.03% wouldn't make that huge of a difference, but it did, okay? Not, I mean, like what, 20 bucks or 15 bucks more, but hey, money's money. And then the last thing we'll talk about is continuously compounded interest. So sometimes you'll see that it'll be compounded continuously, not daily, not monthly, not quarterly, not yearly, but it's compounded continuously. So think about that as like infinity, right? Well, that's where our little guy E comes in. Remember that value of E? That's Euler's number. It's approximately 2.718. That's where it comes to life. This is when it's used in real life problems, is talking about continuous compound interest. So here's what we have for example 5. And notice we have a little bit of a slightly different function to work with. So here we go. It says you have $5,000 to invest. So $5,000 is our principal amount. In an account that earns 1.75 annual interest, compounded continuously, how much money will you have in 10 years? Okay, that's one problem. And then when will you have $7,000 in the account? So this is like problem A, and this is like problem B. So let's start with the first problem. You have $5,000 to invest, 1.75 annual interest, compounding continuously. How much money will you have in 10 years? All right, well, let's write it out. Our final amount is going to be our principal, so $5,000, times e to the RT power. So our R is 0.0175 times t. Well, in this case, t is 10. Okay, so I can plug that into my calculator because remember, e is a number. It's not a variable. So 5,000 e raised to the 0.0175 times 10. I hit enter. My final amount is going to be $5,956.23. So after 10 years, I almost get $1,000 extra just for letting it sit in the bank. Okay. The second question is, when will you have $7,000 in the account? So this is asking a little bit of a different question. Now we know our final amount is $7,000. Our principal is still the 5,000. E raised to the rate 0.0175 times t. This time we don't know how long it's been sitting there to get the $7,000. Okay, by using like kind of common sense, we know that our t value should be more than 10 because in 10 years we only got a final amount of $5,956.23. Now we're looking at a final amount of $7,000, so that's more, so it's gonna be longer than 10 years. Okay, again, this is how you solve, just like the problems earlier on the notes. If you're using your TI, you'll do two graphs, find where they intersect. If you're using your Casio, you'll enter in your formula and you'll do an X calculation, type in that Y value of $7,000 and then it'll give you the X value. So if you want to pause and try to, try that on your own or whatever, but however you figure it out, if you're using the TI calculator or the Casio calculator, your T value is going to be about 19.23 years. So it takes a little bit more than 19 years to reach that $7,000. So letting it sit in the bank for almost 20 years to get an extra $2,000, which, yeah, that is a long time, but it's $2,000 you didn't have in the beginning. All right. Let me know if you have any questions on the discussion board or email or hop on the Zoom conference this week. Okay, bye.